As we push AI agents to perform complex, long-horizon tasks, we are overwhelming them with data. Systems tasked with managing schedules, executing code, and analyzing thousands of files are consistently stalling, hallucinating, or failing completely under the weight of the information we force them to process. The prevailing industry response has been to treat this as a scale problem. Developers assume that feeding highly structured machine data into larger context windows will naturally yield reliable, continuous agent execution. This brute force approach to scaling represents an architectural misconception of how large language models compute. Formatting inputs using rigid machine-native languages like JSON or XML introduces heavy syntax overhead. Every bracket, repeated key, and structural tag consumes precious tokens without adding new meaning, which degrades the system's token efficiency. As the 2 million token capacity bar fills with data blocks, agent accuracy drops sharply, showing a direct negative correlation. Across benchmarks, structured data yields worse execution than plain text. This extra capacity dilutes attention, effectively turning the window into a graveyard for lost instructions. Swapping data formats and paying for larger token limits fails to yield autonomous systems that can operate reliably over time. To build agents that can execute persistent tasks, developers have to identify where the actual cognitive bottleneck is occurring in the pipeline. Throwing raw scale at an LLM results in a bloated, mathematically confused system. It fails to create a persistent agent. Large language models are advanced text prediction engines. They read inputs strictly linearly, left to right, top to bottom. Because they rely on the sequence of incoming tokens, the exact structural layout of your prompt dictates the model's final prediction. In traditional software, developers use formats like JSON or XML because they are strictly parsed by machines. Engineers building AI agents assumed these same schemas would be the most efficient way to communicate with an LLM. This parsing comparison shows why that assumption fails. On the left, raw JSON syntax. On the right, equivalent markdown. JSON's nested brackets and schema labels flash red. These structural elements offer zero predictive value, yet consume strict percentages of the context budget. Markdown delivers the same payload with a fraction of the token footprint. This efficiency translates to performance. Across empirical retrieval benchmarks, researchers find that Markdown ranks as the #1 format for feeding context to agents, with XML a distant second. While Markdown is the current vector, relying on it is just a band-aid over a larger architectural flaw. Even optimized Markdown suffers from a core flaw. It passively fills up the model's memory, which eventually triggers the utilization cliff. The most lean text format cannot overcome the hard mathematical limits of linear token processing when an agent is tasked with running continuously for hours. To address the JSON bloat, the industry attempted an engineering workaround: specialized encoder and decoder token compression. Repositories like Tune have been developed to strip away the structural clutter of JSON. The idea is to keep the strict programmatic schema while discarding the syntax that wastes LLM tokens. Watch how this scanning mechanism processes the data. It dynamically strips away the bloated JSON structural elements, compressing the remaining values into a dense, minimalistic block. This brings the footprint to token parity with Markdown, yet yields no corresponding increase in model accuracy. You can make a rigid data schema numerically equivalent to Markdown, but you cannot force the language model to interact with the meaning of those tokens any differently. Syntax compression shrinks the data footprint. It does not alter how the model processes the intent of the prompt. Hardware efficiency tricks and syntax compression cannot artificially generate long-term reasoning capabilities within an LLM. The failure of formatting solutions brings us back to the physical capacity of the context window itself. Right now, frontier models are marketed on their massive context windows, with systems like Grok boasting the ability to accept up to 2 million tokens in a single prompt. This graph charts context utilization against effectiveness. Notice the vertical boundary at the 20% mark. After crossing it, the performance curve plunges. LLMs achieve peak reasoning strictly within the first 20%. By 60% capacity, the model experiences severe cognitive degradation, high hallucination rates, and missed instructions. This degradation curve is why long-horizon agent systems like OpenDevin or AutoGPT frequently break down. To schedule hours of continual task execution, an agent must log its actions and ingest continuous feedback. This requirement inevitably pushes the system's memory past the 20% cognitive safety threshold. Once it crosses that line, the system experiences agent drift. It loses the thread of its original instructions, overwhelmed by the accumulating noise of its own operational history. A 2 million token window is effectively useless if reasoning only remains accurate for the first 400,000 tokens. Large context windows fail to purchase more reliable compute time. They simply create a larger space for instructions to vanish into the noise of the model's own processing. Since neither formatting nor capacity can overcome the 20% cliff, the bottleneck shifts to the input structure itself. Passive context dumping relies on the model to deduce relevance, a task it fails at once the window fills. This makes the developer's reliance on imprecise, lazy context provision the primary liability for agent performance. The current standard of feeding the LLM a massive block of raw text and expecting it to implicitly deduce relevance is what triggers this failure. We can change this with an @ symbol. It acts as a targeted vector, isolating a specific node and blacking out noise. Explicit intent mapping forces the system to acknowledge dependencies. Like Slack, this mechanic enforces a strict connection to a specific file, eliminating guesswork. This explicit routing mechanic changes how the model processes data, as it creates a direct link between the user's operational prompt and the specific data required for the next step. By enforcing these relational pointers, the system completely bypasses the 20% utilization cliff. The model only receives hyper-relevant, isolated data nodes precisely when it needs them. These targeted intent protocols contrast with the common practice of dumping an entire repository's worth of JSON into the prompt. The next generation of agent harnesses must be engineered to enforce these relational pointers, requiring the system to clarify dependencies before executing a step. AI engineering has to return to software fundamentals: strict intent, explicit purpose, and clear directional communication between the user and the system. Building reliable, long-horizon agents requires developers to take responsibility for explicitly routing intent. We can no longer rely on the illusion of massive scale to solve structural reasoning deficits.